All right, our first question here is, how would you measure the distance from O to segment AB? So O is the center of our circle. All right, this is circle O. How would I measure that? Well, there's a lot of ways you could think about measuring it. If I had like a tape measure, and this is real life, I could hook the tape here. I could measure to here or wherever. I don't know, but what do you think makes the most sense? Something that would be consistent, because we want to be consistent. If you guess that you would measure it perpendicular to that, let's say that this is point C, and I get myself a nice right angle there, you are correct. The way we would measure from O to AB, the distance from O to AB, is measured so that it's perpendicular to that chord. Remember, that's chord AB. All right, so that's how we're going to measure distance. If I say something is the distance from O to AB, it's assumed or it's inferred that it's perpendicular to it. Okay. Now, any other thoughts as to what might occur here if I'm drawing this perpendicular to that segment? What does it look like to you? If you're thinking, hey man, I think these two pieces are now congruent, you are absolutely correct. All right, that segment right there, OC, is perpendicular to and bisects AB. We've talked about perpendicular bisectors before. It's perpendicular to and bisects that chord AB. OC perpendicularly bisects AB. Cool. All right. And we could actually kind of think about that backwards. If I said, hey, this segment, let's say segment XY, if XY perpendicularly bisects AB, then it goes through the center. So if I'm perpendicularly bisecting a chord that's in the circle, I know that it goes through the center. All right. These are all little things that you can use when solving problems with circles. Super exciting, super fun, awesome. All right, so here it says if AB is congruent to CD, meaning my two chords are congruent here, what can we conclude? Well, let's see here. If the two chords are congruent, what could we conclude? Well, I'll lead you guys into this because it's a pretty open-ended question that you might not be thinking, like, well, I have no idea what that to conclude. Well, let's see here. My distance from O to AB is measured when it's drawn perpendicular, right? So this, and the same would obviously go here. My distance to the chord is perpendicular. That's how I measure. Well, what do you think? If I have two congruent chords in the same circle, what do you think is true about their distance to the center? If you said, hey, their distance is the same to the center, you are absolutely correct. So we could write that down. Distance to center is the same. Okay. So if there was a problem and I said, if I just drew it out, say maybe without these congruent marks here, right? If I just had this, and I told you that AB and CD were congruent and that this was 9, then you could conclude that this is also 9, right? Because they are congruent to each other. Okay. So we know that these guys are congruent if my chords are congruent, and vice versa. If I know that two chords are equidistant, and I'll actually type this one. That'll make it a little bit easier. There we go. If two chords are equidistant to the center of the circle, then they are congruent. And that is reversible, meaning, hold up, here we go. If two chords are congruent, then they are equidistant to the center. Bibbidi boppity. Whoop. It just disappeared on me. There we go. Alright, so those two things are excellent to write down. This is just more of a formal representation of what we have here in blue. Okay. Here we've got if AB is tangent to circle O at C, what can we conclude? Remember, tangent just means that it's touching at that one spot, okay, just at C. It's just resting on there. Imagine a tire sitting on the ground, right? It's touching at that one spot, other than like if it's being pushed down. But imagine a tire that does not flex at all. It's touching at one exact spot to the ground. Okay. Well, what can we conclude? Again, a very vague question, but let's talk about it. Well, what do you think? If I draw from the center to C, what do you think is true? And actually, I'm going to use a real line here. Let's see if I can get one up, because that'd be way more fancy. What do you think is true about that line segment, the radius, okay, and segment AB? Well, if you guessed, hey man, I'm pretty sure those are perpendicular, you are absolutely correct. They are indeed perpendicular. All right, so when you draw a line that's tangent to the circle, it's perpendicular to the radius that touches at that point. Awesome. That can be very helpful to solve things, because you can break things into right triangles and all sorts of great stuff. Okay? Cool. All right, next one here. You got AB and BC are tangent to circle O. What can we conclude? Well, I guess as a general recap, we know that these guys are perpendicular, and these. Whoop, oh boy, didn't mean to do that. And I just wanted to draw another line, segment, and those guys are congruent, right? So those guys are perpendicular, right? So I know that. That was from the last one, but what else could I conclude? What do you think about this segment and this segment? If you're thinking, hey man, I think that those guys are congruent, you are 100% absolutely correct. Okay. Now, one other thing that I'd like to maybe bring up as well for us to ponder. What if I created this ABCO? ABCO. That's a quadrilateral, isn't it? Okay. And how many degrees are in a quadrilateral? 360 degrees in a quadrilateral. But I can't fit that. Okay. Well, two of those are already 90 degrees, so what's left over? 180 degrees left over. Okay. Well, what else can we figure out? What do you think we know about maybe this angle and this angle? Well, if you're thinking, well, those add up to 180, so basically they're like supplementary to each other, you are absolutely correct. Angle O, the central angle, and exterior angle, referred to as the, hold up, to tangent, are sup. And to go even further, like, so say if I knew that this was like 120, then I know that this guy is 60, because they add up to 180, right? Cool. Now I want to go a step further. What if I knew something like, what if I knew that this arc right here, let me go in purple now, get another color up. If I knew that this arc right here was, say, so the measure of arc AC was 115. Now what would I know? Well, I got my central angle. This is 115 because it's the same, right? And voila, this is 65. So that that arc could also kind of join in on the information here. I'm pulling in things from the past couple videos as well, so you got to remember all that stuff. It all comes into play here. All right, so that's enough for properties and fun facts and definitions and all that good stuff. Let's try a practice problem here. It says find the measure of angle B. So I want to figure out what this guy is. If the measure of arc AC is 145. So this arc right here is 145. Okay. Well, if you were paying attention to the problem previous to this, right, before this, we know that if that's 145, I know that this is 145, and I know that this is going to be supplementary to that, right? So I would get 35 degrees. You also could have figured that out from the previous video because we know that these guys are right angles. So I've got 180 degrees right there, and there's 360 in a quadrilateral. Subtract out 180. I'm left with 180 for both this angle and this angle right here. Okay? So there we go. Bippity boppity, pulling in central angles, pulling in all sorts of fun stuff. But yeah, 35 would be my answer for this one right here. And this is called a two-tangent angle because it's created by two external tangents. Awesome. All right, here we got to find the distance from the center of a circle to a chord, 30 meters long, if the diameter of the circle is 68 meters. Okay, that's interesting. Well, let's draw a chord in here because that's a thing to do. That looks good. And let me position that a little better. There we go. I like that. Okay. So let's say that chord right there, it says that it's 30 meters long. All right. And then it says find the distance from the center of a circle to a chord. So what I'm looking for is from here to here. And I know that the distance is perpendicular. So that's what I want. Okay. And it says the diameter is 68. Now, what most will want to do here is they'll be like, okay, well, let me draw this diameter that's 68 meters. But what the heck does that do for me? Let's think a little bit more about this, okay? Rather than doing that, let's think a little bit more. Well, half the diameter is a radius, right? So the radius is equal to 34 because that's half of 68. Couldn't I draw a radius like this from the center to the edge of the circle? I think so. And what do I know about if I draw a line from the center perpendicular to a chord, it's going to bisect that chord. So that's going to become 15. Oh, yeah. So now, what happens? Oh, my goodness. We've got ourselves a right triangle here, guys. Oh, what do I need to use? I'm thinking a little Pythagorean Theorem. We got x squared plus 15 squared equals 34 squared. All right, well, I'm not going to do this all in my head here. Let's see here. We've got 15 squared is what, 225? Yeah. X squared plus 225. And then 34 squared gives me 1,156. I'm going to subtract that 225. I get 931. So I get x squared is equal to 931. Okay. And then I don't think I can really simplify them. I'm not even going to mess with that. But let's take the square root of it. So I'm going to get x is equal to, if I square root, 30.5, roughly. So I'm going to make those squiggly equals. And that's meters. All right. That's my distance to that chord. So brought in Pythagorean Theorem. A blast from the past, if you will. Last problem here. A quadrilateral is circumscribed about a circle. That's a new word, children. Okay. If it has side lengths 8, 10, and 11, find the fourth side length. Well, what the heck does it mean to be circumscribed about a circle? That means that the quadrilateral is actually on the outside. And I'm going to try and do my best here to make a lot of tangent sides. So when it's circumscribed about, that means basically on the outside, this quadrilateral is tangent to the circle at 4 spots. Okay. I'd say a decent job there. I'm pretty happy with what I got there. So it's tangent at these 4 spots, okay? And it says that we've got side lengths of 8, so we'll say this guy is 8, 10, and 11. And I want to figure out what this is. I don't know what it is. Okay. That's my unknown. That's what I want. Now, how am I going to figure this out? This is interesting. So I don't have a whole lot to go off of here, which can be tough. Well, because I'm a math genius, I think I can figure something out. And I will guide you down the path of geniusness. Okay. Well, I know from my two tangents, right, from an earlier slide, that these will be congruent, these will be congruent, these will be congruent, and these will be congruent. Okay? So all my two tangents will be congruent to each other. So I'm going to start off as with this right here to be y, which would make this y right here. Okay? Right? They'd be congruent to each other. Would you know, right? Yeah. If one of them's y, the other one's y. Well, what's left over for just this portion right here? If the whole thing is 10 and this part is y, I could do 10 minus y to get this, right? We got to think kind of in an abstract way. So this right here is 10 minus y. And since that's congruent to this guy, it would apply to that one as well, right? Okay. So we're getting somewhere. Could I apply the same concept on the next one? It's going to get a little messier, but that's okay. If this is 10 minus y, and the whole thing is 8, I would need to subtract this out of 8 to get this. So it would be, and I'm going to jot this off to the side here, 8 minus 10 minus y. Got to have these parentheses because that's going to distribute my negative. This is algebra now. So I'm going to have 8 minus 10, which is negative 2, and negative times negative makes it positive y. Alrighty, so I have negative 2 plus y for this guy and for this guy. So let us continue. Do I have anything else that I go with? Well, I don't know this next part. I'm going to pop back up over here, right? Because I know if this is y right here, then this would be 11 minus the y. Okay, so 11 minus y. And since that guy's congruent to this guy, 11 minus y for this as well. So this whole side is 11 minus y and negative 2 plus y added together. 11 minus y plus negative 2 plus y. Think about why that makes sense, right? Well, if I have two lengths of segments that create the entire segment, I could just add them up. I know the y's are scary. It looks weird with the variables. This is very mathy math. But think about the general idea. We're adding two segment lengths together to get the full thing. These cancel out. I'm left with 11 minus 2, which equals 9. So 9 would be my fourth side length. That is a cool problem. We often call it a walk-around problem because we have to walk around the problem. We'll try a couple more of those in class, I am sure. They're also in your homework packet. Have a lovely day.